Fermi's golden rule is one very useful result in time-dependent perturbation theory, though to illustrate its use we would need to set up some system quantum mechanically that has the required dense set of possible transitions. We'll have to postpone that specific use for some later time. However, there's another particular problem we can look at for which we can write down quite a general result for a simple oscillating perturbation, and that's the calculation of refractive index. Refractive index tells us how fast light is going in some material. Specifically, the phase velocity of light is inversely proportional to refractive index. If we have a refractive index of 1.5, which is roughly the refractive index of a typical glass, for example, then in that material the phase velocity of light is 2/3 of the ordinary free space velocity. How, though, can we calculate the refractive index from quantum mechanics? Well, we'll show here how to do that. We'll need to set up some standard relations from electromagnetism. If you don't know those already, don't worry. We'll simply state them here and then proceed with the quantum mechanics.
So let's see then how we can calculate this perfectly real quantity that we encounter with materials, one which it's not at all obvious how we could figure it out from looking at any classical model of materials. So this is a serious exercise in how quantum mechanics can actually help us calculate real things about materials. In classical electromagnetism, when we apply an electric field to a material, we can imagine that the field pulls the average position of the negatively charged electrons away from the average position of the positively charged nuclei inside the atoms. And that would create what is called a polarization, and we could give that a letter P here. So we've polarized the electrons and nuclei in an atom, for example, by applying an electric field and pulling the electron and the nuclei in opposite directions. Now, at least for applied fields that are small compared to the fields in the atoms themselves, we would expect that this polarization P is approximately proportional to the applied field. So, with some proportionality constant here, we'll call that the susceptibility, chi, and that's a dimensionless number. For historical reasons, a fundamental constant is also involved, and this is called these days the electric constant. It used to be called the dielectric constant of free space. It's a number with dimensions to it, but it has no real physical significance. It's just there because of the way that units were developed historically in electromagnetism. So with that minor change here, we write the polarization is this electric constant times chi times the electric field, and this chi is the susceptibility, a dimensionless quantity. Now, in the classical view of electromagnetic waves, the fact that we are moving these electrons with the oscillating field means that we have a new oscillating current. We're moving these electrons, and that current itself generates new waves. And this is incidentally a theory we could look at explicitly quantum mechanically as well. These new waves we are generating add together with the original waves to give us a new total wave. They interfere, as it were, with the original waves. And the net result of that is that the effective phase velocity of the total wave is changed. That's because the new waves that are generated are not actually quite the same phase as the waves that created them. Now, this is understandable in a classical sense in a made-up model of a material that consists of little electrons on springs. That's not actually how materials are made, but we could construct a theory on that basis and get this current. And anyway, if we propose we have the current, we can certainly calculate this phenomenon. And formally then, we would have come up with the refractive index because the phase velocity would have been divided by this refractive index, which we'll call nr. Now, if we follow through the classical electromagnetism of this problem, which, for example, we would use Maxwell's equations to derive, we can conclude that, at least for non-absorbing materials, or to be more precise, materials in regions, spectral regions, where they are not absorbing, then that refractive index would be given by this formula. So if we know the susceptibility, we could calculate the refractive index, and it happens to be the square root of 1 plus the susceptibility. As I say, to prove that, we'd need to look at some classical wave theory for electromagnetism, but it's very standard. Hence, if we can calculate the proportionality between the polarization and the electric field, that means we can calculate this constant chi here, then we can calculate the refractive index for some material. Well, let's consider a system with a single electron for simplicity, or at least one in which our interactions are only with a single electron. Classically, there's a quantity called the dipole moment, so we've written that with the Greek letter mu and a subscript dip for dipole. And that's associated with moving a single electron through some distance z. And by definition, that dipole moment is given by minus e times that distance z. And the minus sign here is simply because the electron charge is negative. Well, the polarization then, P, is formally defined as the dipole moment per unit volume. So we might imagine that we had a lot of atoms inside some volume, and each one of them was polarized with this little dipole moment, and then the polarization as a quantity would then be formally defined as the dipole moment per unit volume. And so the quantum mechanical expectation value of the polarization is something that would look like this. It would be the expectation value of the position of the electron multiplied by the electronic charge, here with a minus sign, and divided by the volume in which this electron system was sitting. Our quantum mechanical task now of calculating refractive index reduces essentially to calculating the expectation value of P, which is really in the end the expectation value of Z, in the presence of our perturbation, that is, our applied electric field. We're working in first-order perturbation theory, so we can write the approximate total state of the system as a sum of the unperturbed system plus a first-order perturbation. And we could have put a gamma in here. We're presuming now that we don't need that particular trick stated explicitly, although we could put it back in if we wanted to. So if you're worried about it, you could put the gamma back in here to keep track of the orders. Note we're going to use full time-dependent state vectors, or kets, here. So as I said, phi naught, the capital phi naught, is the unperturbed state vector, and capital phi 1 is the first-order time-dependent correction to that. And, of course, from our perturbation theory, we know what that is. If we can calculate these expansion coefficients here from our first-order perturbation theory, then this whole ket here for the first-order time-dependent correction to the wave function will be given by this expression. It's just an expansion. And the unperturbed energy eigenvalues, En, of course, are associated with this omega n here, and the eigenfunctions are psi n. The energy En is just h bar times omega n. Well, with this state vector, the expectation value of the polarization would be as follows. We just have to take the actual state as a bra vector, the position vector z, and the state as a ket vector. And of course, we've got these dimensioning constants out front. Well, formally, we can write that out. We can take the product of this pair of functions here as ket vectors and the pair of them as bra vectors, so substituting for these psi's, and we'll get 4 terms in our product of these pairs of 2 functions. Well, this first term here is just what we could call the static dipole moment of the material in its unperturbed state. So that's not particularly interesting to us. It's just a constant static polarization that the material might have. So we're not going to consider that term any further. So we can grey that out, which is what we've done here. The fourth term here, well, you'll see that's got a phi 1 in it and another phi 1 over here. This is really a second-order term in our overall perturbation. Remember, we could, if we wanted to, put a gamma with a phi 1, and hence we would have another gamma with this one, and this would be a term in gamma squared. And overall, that's a second-order term, and we're only doing this calculation to first order, so we'll throw that one away. We'll drop that one. you can see by contrast that these terms are overall just first order in the wave function. At least we could think of there being a gamma associated with this phi1 and a gamma associated with this phi1. So we're left with just two terms in our expectation value of the polarization to first order in the perturbation here. But because this operator z is a Hermitian operator, then this bra operator ket is equal to the complex conjugate of this one. That's actually a definition of Hermiticity. And therefore, the polarization is actually equal to twice E over V, with a minus sign, the real part of this particular object here. Because an object plus its complex conjugate just gives us twice the real part of the object. For the sake of definiteness now, let's presume we start in a specific eigenstate m. So therefore our starting state is psi m here, and we've put in our time factor. Hence, using the first order perturbation expansion from this expression here, we have that the expectation value of the polarization explicitly now should be all of this expression. Now, we are interested here in a steady state situation, so we don't have to take quite the same approach as we took when we were working towards Fermi's golden rule of having a perturbation on for a particular period of time. Here we can just leave the perturbation running all the time. So we can have a continuous oscillating field, and therefore we can simply take our perturbing Hamiltonian to be the same one as we saw before, but actually going on forever if we like. We don't have to put bounds on it. So we take it to be valid for all times. And then we can rewrite this equation as this equation here, where we've explicitly put in our perturbing Hamiltonian as before. And now, in this case, we have the z inside this matrix element here. We've taken our electronic charge and our field magnitude out here. And this, of course, came from our oscillating field that is built into the perturbing Hamiltonian. And then we will obtain from that, by integrating, we'll obtain this expression here. And because the field's been on forever, this is a little bit simpler than what we encountered with the Fermi's golden rule derivation. So, substituting this answer for the expansion coefficient of the qth state to first order into our expression here for the expectation value of the polarization, so we're simply substituting this in here, then we get an expression that looks like the following. So we have a square of this matrix element inside here because we had one from this and there's one in here already. We have this exp of I omega mn t in here, and then we have these two terms in the overall result. Now, incidentally, just algebraically, note that omega mn is just minus omega nm, which allows us to simplify the signs a little bit. And then remember, we have to take a real part here. That was in our formula. So taking the real part, we end up with cosines here instead of the complex exponentials. And noting now we're writing in terms of omega nm, that takes care of another one of our sines that we would otherwise have had. And so here's our expression for the expectation value of the polarization. And note that out here we have E naught cos omega t. And that is actually, with the 2 in it, the original field that we applied to this system. So from this expression that the polarization is, by definition, the electric constant times the susceptibility times E, then the susceptibility now, we can just cancel the original driving field, which was all of this here, with the cosine, 2 E naught cosine omega t. We can cancel that out, put the epsilon naught on the bottom line, and here we have our expression for chi. So if we started in some state psi m, at least conceptually, that's the starting state of the system, but we have this perturbation just running all the time, then we're going to find a polarization that is proportional to the modulus squared of that matrix element for each of the possible states of the system, with these denominators built in here as well for each of the possible states n of the system. So this susceptibility is something where we have a sum over all possible other states of the system. So if we can do this calculation, then we can calculate our refractive index. And that would complete our calculation of refractive index. Hence, if we know all the unperturbed energy eigenfunctions, basically these psi m's or the psi n's, and the eigenvalues, which allows us to figure out these omegas in here, omega nm, for some quantum mechanical system, we can calculate the refractive index that that material or system would have. And we've done that using time-dependent perturbation theory. So we've been able to use time-dependent perturbation theory to calculate a perfectly real property of a material. Now, there's a key difference that you'll note here between absorption and refractive index. For absorption, the frequency omega must match the transition frequency very closely. In our theory, it was turning into a delta function. It might well be a Lorentzian function, the matching we have to have here. But still, the frequency of the radiation must match the transition frequency very closely. Otherwise, that particular transition will not have absorption of photons associated with it. But for refractive index, the contribution of a particular possible transition from, say, psi m to psi n to the susceptibility, and hence to the refractive index, is finite even when the frequencies do not match exactly or even closely. That contribution to the susceptibility rises, of course, because of those denominators we saw in our expressions, as omega rises towards omega nm, for example. Note that if we have an absorbing transition at some frequency omega nm, it contributes to the refractive index at all frequencies. If we go back and look at our formula for the refractive index, it had these matrix elements in it, the same ones that we found in the absorbing transitions, in Fermi's golden rule. There we had to match the frequency very well to get absorption, but the refractive index is saying if you have the possibility of absorption at some other frequency, then you will have a refractive index contribution from that. Refractive index, in a region where the material is transparent, arises entirely because of the possibility of absorption at other frequencies. That might sound a very strange thing. We're not actually doing absorption at those other frequencies, at least not in any steady sense. There's no net transition rate here. This perturbation is running continuously and the state of the material is not really changing. But nonetheless, the refractive index arises because it would be possible to have absorption at other frequencies. A rather strange idea. If there is a refractive index different from unity, then there has to be absorption possible at some other frequency or frequencies. Those other transitions have to exist at some other frequency or frequencies. So this works both ways round. The relation between refractive index and absorption is actually quite well known from classical physics in a mathematical sense, through what are called the Kramers-Kronig relations, and I won't state those here, although they're easy to look up. The derivation of these relations is almost entirely a mathematical exercise and does not tell us much about the microscopic physics of why these arise. And that's in part because in classical physics we don't really have any good model of materials. So all we have is this mathematical relation here, a very useful one, but little physical insight as to what's going on. So that mathematical approach from classical physics really does not help us understand the physical mechanism whereby absorption and refractive index are related in a real material. On the other hand, with our quantum mechanical expressions, we can understand any particular aspect in the relation between these two processes. In the quantum mechanical picture, we find that even though we are in a transparent spectral region, there are finite occupation probabilities for all of the states of the system. And that might surprise us because we're not thinking there's any absorption going on. but nonetheless it's true. And these are essential if the material is to have some polarization in it. It's almost as if when you took your glasses out of their case in the morning and put them on, at that point perhaps we might imagine somehow the glass becomes excited, and there are these probabilities of finding the glass in excited states, but that remains fairly constant throughout the rest of the day. Incidentally, these probabilities for particular states are not very large, but they are also certainly not zero. The polarization arises because the charges in the material change their physical wave functions in response to the field, mixing in other states of the system in response to the perturbation of the light shining through the glass. If indeed we examine the expectation value of the energy of this material, your glasses with light shining through them, or your lenses in your eye with light shining through them, you would in fact find quite real energy stored in the material as a result. And that's true even though the material is transparent.
So now we've demonstrated that we can calculate a useful property of materials using first-order time-dependent perturbation theory, the refractive index. At this point, we've essentially set up the kind of theory that, if we wanted to do so, would allow us to continue to calculate nonlinear optical effects by simply proceeding here to higher-order time-dependent perturbation theory, for example. Though we'll have to postpone any such discussion here.